Okay, there we go.
Perfect.
So next talk is about a C++ DSL for flexible tree rewriting, and our speaker is Matilda Blomqvist. Go ahead.
Yes, so I'm Matilda. I'm a PhD student at Uppsala University, and I will present this joint work by Uppsala University and Microsoft Research. And as the title suggests, Trieste is a C++ domain-specific language for tree rewriting. And since this is a tool paper, I will mostly focus on what we can do with Trieste. And its main intended use is to write multipass compiler. So this could be a generic compiler pipeline where we have multiple passes. We do some modification to the abstract syntax tree in these different passes. So one problem that arises when we have multiple passes, we might also need to change the intermediate representation between the passes. So for example, consider this Haskell data type for a small imperative language. And we want to write a type checker, but we have no type fields in this data type. So one alternative could be to just update the type the data type we already have with option type. So there may be type in Haskell or a nullable field in C++. But the problem is that then we can't statically know where we have type information or not. So we need to always validate where we have types. So another alternative would be to define a new data type, so that the type checker basically translates from one data type to another. And then we statically, of course, know where we have types or not. But it introduced a lot of code duplication and boilerplate. And of course, we're not the first one trying to mitigate this problem. In object-oriented languages, we can do visitors or listeners or smart subtyping things. And in Haskell, we, for example, have trees that grow. But each solution comes with its own trade-off. So in Trieste, we have something that we call flexible trees. So these two abstract syntax trees actually represents the same expression, the 1 plus 2 plus 3 plus 4. But they have the same static data type. So how is that possible? So the tree type in Trieste is just, a tree just consists of nodes that have a token, and the token can be seen as the type of a node. And we have two different types of tokens. We have built-in tokens, so for example, this generic group token that we will see is added by the parser later. But most of the tokens are language-specific and defined by the language implementer or the compiler developer. So the expected structure of the tree is not described by the tree data type. It can be changed in every rewrite pass without having to define new data types or visitors. So if we don't have types to describe the dynamic structure, then what do we have? We call this well-formless specifications. So, and the well-formless specification you can see in the top right corner, and it can be read as a group node should have one or more children, that is one of the choice in the parse token, and a parenthesis node can have one group node as child. And I'm apologizing beforehand that we make heavily use of C++ operator overloading, so you will see more of these operators later. And then you might wonder, but isn't that just the same amount of work we need to define well-formless specification instead of defining data types? So we argue it's a bit more simple. So, for example, consider that we want to rewrite the addition nodes here such that they are parents of their operands. And we need to specify a well-formless that like capture this rewrite. And then we can start from the previous well-formless of the tree that we started with. So yeah, we start from the previous well-formless, and we just add a new shape for the new structure that we have added. So this was a generic compiler pipeline, and this is more a description of the Trieste pipeline. So we start with lexing / simple parsing, and we will see why we call it a simple parser in a bit. And then we continue with multiple rewrite passes. And both the parser and each pass in Trieste have this well-formless specification that we check dynamically between each pass. So very quickly, an overview of the Trieste program. So we parse some source code into an initial abstract syntax tree. We can check for parse errors in the tree. If we find one, we report it. Otherwise, we check that the tree conforms to this well-formless specification. And if it doesn't, we report a well-formless error. And the difference between those two kinds of errors is that the first one is what you normally would think of as a parse error or compiler error. So it's a mistake in the source program, while the second one suggests a mistake in the implementation itself. So it's more of a tool for you as a compiler developer. And if everything is fine, we apply the next rewrite pass, and we check for errors in the updated tree. And this process continues until we have no more rewrite passes to apply. So to get you a better feeling for how we can use Trieste, let's write a compiler frontend in Trieste. So what do we need? We need a lexer / a parser and a well-formless specification. We need some rewrite passes and well-formless specifications for each pass. And we need a language in mind. And in my mind, I have MiniML, which is a minimal subset of standard ML. So this is an example of the factorial function in MiniML. And as any good TV host in a cooking show, I've already prepared this compiler frontend beforehand. So the trees we saw before actually come from this Trieste implementation of MiniML. So the left tree is the initial parse tree produced by this simple parser, and the right tree is the syntax tree for the same expression, but after the final rewrite pass, where we also have inferred types of the expressions. So to start with, how do we obtain the first or the initial tree? So a parser in Trieste consists of parse rules that contains a regex and what we call a parse effect. So this is a C++ lambda function for those of you not very familiar with C++ syntax. And the effect basically maps a token to, or maps a parse action that can take a token and can be inserted into the tree. So this can be read as match a number and add an integer node with the number as a value into the tree. So if we look at this example, this very simple expression again, and how we could parse that expression, we only need this rule. The actual parser has, of course, more rules. But you don't have to read these rules very carefully. I just wanted to show that, for example, if we used the addition parse action, we just insert the tokens to the current group. And we just saw that white space is a no-op. But for example, for parentheses, we want to add more structure immediately, because just using add would essentially give us a single large group of tokens, so it would be essentially a lexer. But we can do some more structures. So for example, when we use push, as we use in the, for the parentheses rule, we actually, you can say we move the cursor inside, and any subsequent adds will be added into a new group inside the parentheses. And when we find the closing parenthesis, we don't add any new tokens, we just terminate the group and the parenthesis node. And we can finalize the initial parse tree. And as I said, every pass needs its well-formed specification. We are actually already seen this well-formed specification and this tree, and we saw that it was well-formed. So then we can continue with our rewrite passes. Because we don't have a lot of structure into this tree, so we need to, or we want to continue parsing by rewriting. But first, just update our example to something slightly more interesting. So also using a let expression and a multiplication. So say that we want to rewrite this parenthesis nodes with a group inside to just be an expression with this addition expression inside. We can look at the rewrite rule we have defined for this. So a rewrite rule consists of a pattern that we can match against a subtree and returns an effect, which is what we will replace the selected subtree with. And rewrite rules are applied at all positions in the tree. Yeah, let's start look at the pattern. So this can be read as match a parenthesis node with a group node as the first child. So just a note on syntax, the T is a pattern constructor. This operator can be read as is parent of, and we can use the brackets to attach a label to a pattern. And this is an example of a subtree that could match this pattern. And I just wanted to show you some other patterns to show the expressivity of patterns. So we could also match, for example, an expression followed by an expression with an add node as child in an application node, in an expression node, in a top expression node. We can repeat patterns. We can have context in patterns. So for example, we have different pattern predicates. And we can have deeper context. So that aside, we come back to our example and the other half of a rewrite rule, namely the effect. So this effect could be read as return an expression node with the same children as the matched group node. So here we have overloaded the brackets to access a node with a label. And we can retrieve the children from this node and add it to a new expression node. So in action, we can see that we will have this resulting tree. Yay, we already defined our first rewrite pass in Trieste. But we have only seen a single rewrite rule. So that's a truth with modification. So this is actually the full definition of the parenthesis pass. This is the rule that we just saw, but we also have two more rules in this pass. So we can call those error rules that we can use to signal if we find any mistakes, any remaining parentheses that have not been rewritten. And as you can see, error is another type of built-in tokens in Trieste that we can use to signal errors. Having the error nodes directly in the tree also makes that we can see exactly where in the tree an error occurred. A pass also has a direction of traversal, so we can traverse the tree in different order. And as I mentioned, we also have a well-formed specification. So We can also see here that we amend the well-formed specification from the previous pass, in this case a pass that rewrites functions. We remove parentheses, so they are no longer valid nodes in the tree. And we add, since we added expression nodes, we need to add a new shape for expressions. So this is all the rewrite passes we have in the minimal compiler frontend, and we can categorize them into passes that do more parsing and passes that do type inference. And we will just see a few more examples of the parsing passes just to see how the tree evolves. And that the rules that we use to do that is not very complicated. So for example, the next path is to restructure let bindings. And if we look at the well-formedness first, we can see that if we start from the well-formedness for the parentheses pass that we just saw, we just want to add new things. We don't want to change anything. We need to have let expressions that have an identifier and an expression. And at this point, we also know we can say something about the structure of the whole program, since MiniML only consists of let bindings and expressions at top level. So the rewrite rule looks something like this. So once again, the details are not important, but we can see that we give a lot of more structure to the tree immediately. We also have a pass, the next rewrite pass just rewrites simple expressions, so for example, integer expressions, and wraps them in expression nodes. And here we can see an example of a rule that matches in several places in the tree. Yeah. We also have passes for binary operators. So for example, multiplication is handled just to restructure the operands as its children. We have a very similar passes for additions and subtractions. And note here that we need to rewrite multiplications first because of operator precedence. So now we have quite some more structure to our tree, and the remaining parsing passes just this for comparison binary expressions and some cleanup. So let's look at a more interesting example. So infer expression is a pass for generating type constraints and to type expressions. So we can start with a very simple rule that just types integer expressions. So we just add a type int to the integer expression, and this will, of course, reapply it to all integer expressions. And when we have done that, we have subsequent rules in this pass that can also type compound expressions. So for example, the addition and multiplication expression here. And we see that the rule immediately gets a bit more complicated. We can do arbitrary C++ in the effect. So I don't want you to necessarily read this. We can read this as match a binary expression and its operands, and with the effect that we want to create and lift type constraints on the operand types and set the type of the expressions to an integer. So if we start with the second part, we add the type to the expression. And then we have machinery to lift nodes to a higher context. So here we have created a equality constraints for the operand types. So in this case, both types already have type int. So it's a, kind of trivial constraint. But yeah, that might differ on a more complicated expression. So we also have support for scoped symbol tables and variable bindings, but that didn't really fit into this talk today. So we have seen that the order of the passes matters. So for example, we saw that the multiplication pass comes before the addition pass because of operator precedence. And we have also seen that the well-formed specifications can be seen as post-conditions of a rewrite pass. But of course, it can also be seen as a precondition for the subsequent pass. And this also makes the well-formed specification suitable for generating random trees for FOSS testing. So we also use these specifications to FOSS test our programs. So for example, starting fuzzing from the addition pass, we would start by generating a tree from this well-formed specification for the multiplication pass, then apply the rewrite, and the first check we will do is that the tree conforms to the addition well-formed specification before we continue with the rest of the rewrite passes. So what happens when we have applied all of our rewrite passes? The tree for our running example would look something like this, and here I've normalized the well-formed specification so it not builds on previous well-formed just to show the full specification. And we can see that here it much more, if you squint a bit, it much more resembles a data type definition that is, well, when you have learned to read these operators, is actually quite readable. So to wrap things up, we have some existing Trieste developments. So there's a JSON and YAML parser with a YAML to JSON converter. There's a C++ interpreter for the Rego policy language that is built on top of Trieste. And we have the Verona programming language that is currently developed in Trieste. So quick summary, a Trieste program, you can write a Trieste program with just defining some tokens, a parser, a sequence of rewrite passes, each consisting of a collection of rewrite rules. It has a specified direction of traversal and a well-formed specification. So what does all of this give us? So we have seen the flexible trees. It gives us minimal boilerplate. So for example, all a Trieste program fits in this box. We don't need any visitors or listeners or other mechanisms around it that we need as a compiler developer to implement ourselves. The system is quite extensible. The parsing rules are easy. We can easily add new tokens, and we can decide when we want to do something more with them in a rewrite rule. So it makes Trieste good for example, language prototyping. We have quite expressive pattern matching, which is quite important since we don't have any static type to describe the tree. And we get fast testing out of the box. Thank you for listening. This is a link to the paper if you want to find it.
All right.
Thank you. Very, very interesting work. My question is about the kind of patterns that you can express.
Yeah.
So if I understand correctly, if I wanted to, for instance, pattern match everything that has type int, then I would look for something that has a node's type t-int,
yeah.
right? But that means that all the properties that I want to put in my nodes, I need to express as additional nodes in the tree? Or can I have like other properties? Because I'm concerned that some properties might be difficult to express as just trees, right?
Yes, that's a good question. Like, of course, some properties might be more difficult to express as just a node in the tree. So currently, there's no way to like store other information than just basically the value of an integer in a node. But you can make other analysis since you can always do like arbitrary C++ on the side if you need to do more complex things. Yeah.
But would there be a way to reuse? Then I guess, is there a way to just reuse the pattern matching machinery to then not do a rewrite, just get me the list of nodes that satisfy this pattern, and then leave me alone. I would do my own cuisine.
Yes, of course, we can pattern match outside of a rewrite rule, but currently the way of doing that is less straightforward than, syntactically less straightforward than using it in a rewrite rule.
Thank you.
So how does it compare to something like Stratego?
That's a good question. I mean, the purpose of the tool is quite similar. We want to help a tool that helps facilitating in compiler development. I guess Stratego has more concretely separated DSLs for the different steps that you want to do, as of my understanding of Stratego. But yeah, I'm not sure exactly what limitations Trieste has compared to Stratego, or yeah. I haven't used Stratego myself, so my understanding is that we have different DSLs for doing different things, and here, as I tried to show with the Trieste pipeline, most of the things we do in Trieste uses the same DSL. We do pattern matching and rewriting.
Thank you very much for your presentation. So you've shown how you can modularly extend the compiler pipeline using your approach. Could you reflect on the extent to which you can also let a language evolve modularly, so add new language constructs? To which extent can you just add new code, or would you have to modify existing code?
That's a good question. So just to add new syntactic constructs to the languages, I mean, then you need to define new tokens, and you need to define a parse rule to get the tokens into the initial tree. And then, since all the well-formed specification builds on each other, so if you add, for example, if you add a shape for this new token in the first well-formed specification, since they build on each other, you can choose when you want to do something more with this newly added syntactical constructs, or whatever we want. So it depends on how large the change is. I would say you could introduce new things into a language without needing to rewrite much code. But I guess if you want, if it changes also other structures that you have already defined, or if it just inserts something and then the rest of the structure is the same, then I don't think the change would be very invasive.
All right, let's thank the speaker again.
Yeah.